is now about six years old around kinetic architecture. And my interest in the topic was kind of twofold. As one, I lead a sustainability practice for an engineering firm, Arab. I've actually done work in India through that practice, including the new U.S. consulate in Hyderabad, which I believe is in construction currently. But my interest in sustainability is really focused on reducing energy costs associated with building and improving the indoor environmental quality of buildings. And then, the other side of it is sort of my interest in technology and building technology. And so bringing those two together and thinking about buildings that can adapt their relationship to the environment in an active way is where the research started. And what I wanted to do was sort of create a book that would look at kinetic architecture as an emerging design technology in architecture, and understand the benefits that an active envelope could have in terms of building performance and the quality of those internal environments. And the sense is that as electronics and control devices become more prevalent in society and become something that is cheaper to produce, that architecture needs to orient itself to use that technology in a productive way. And so the book is mostly case studies of projects that sort of attempt to do that. So just really quick, like I was saying, I work for Arab. We're a global company. We actually do have offices in India. Some of our projects that we've done, these are two projects in San Francisco, California Academy of Sciences, the De Young Museum. We work on a lot of projects that I would say with kind of leading edge architects who are pushing design. This is the CCTV tower in Beijing with OMA. So just a few projects, just to give you a flavor. This is a project I've been working on for about 12 years. The Guggenheim Abu Dhabi with Frank Gehry is a Los Angeles architect. So that was just a quickie introduction. So what is the opportunity of kinetic facade? So the opportunity is that we live in a world where climate change is really the defining event of our lives. It will certainly be the defining event of your practice after college. This is looking at different climate types in the world. Climate is something that changes, that is changing before our eyes, but weather is something that changes every day. And yet our buildings are a static element within this very dynamic system. And so, we know, I have worked in sustainability a long time, so I tend to be more toward the cynical side around climate change. I feel like climate change is only all of the worst case scenarios will probably occur because we're not making changes fast enough to reduce global temperature changes. The other thing is that buildings, where are the costs in a building, right? The design cost, your fee as an architect is the tiniest part of the entire cost model of architecture. So capital cost, which is say like the cost of construction, is also one of the smaller aspects of a building, and then maintenance costs being the next significant impact. But the running cost of a business is by far, and that's the value associated with all of the people who occupy that building. And let's think about this as sort of like an office building. The costs of an office building are really the people that are inside of it. And so anything we can do as designers to improve the quality of the experience for the people who occupy the building will pay itself back over the life of that building, time and again, right? Way more than cutting the architect's fee. So this is a great argument for us to make, because we can tell the owner, look, if you spend more money and make this building more adaptive to and flexible to changing conditions, it will pay for itself. So this, to think about kinetic architecture, you have to also think about process, and it's an important to lay out a design process that is going to support that as an outcome. And so I show this kind of generic slide that kind of talks about evolutionary design parameters, and that when I think about the envelope, I'm not coming to the table with the architects we work with a set idea. I'm coming to the table with a set of criteria that we will play with, right? And that the criteria could be things like the window to wall ratio, right? The percentage of glazing to opaque area. It could be the different glass types in terms of U values and solar heat gain coefficients. It could be different configurations of glazing, but then and shading devices. But even within the design of a shading device, right? If we're thinking about a kinetic shading device, say, even like a shade that just moves up and down, or a screen that moves back and forth to go from 60% open to 20% open. These are all stops along the way in terms of a control process. And so how we can set up an evolutionary optimization process to look at all of this multi-criteria design in multiple scenarios, and then optimize around what the best outcome is. So the reason this is complicated, right, is because a facade has to do so much. An envelope does so much for our building. In a cooling dominated climate, a facade has to reduce the solar heat gain. It has to also allow daylight into the building. Otherwise, people will go crazy if they can't see the sun, right? It has to control for glare when it allows that daylight into the building. And the solar heat gain component has two aspects to it, right? It impacts the mechanical system that we might have in our building to reject that heat. It deals with the humidity aspect of that, perhaps. But then it also affects thermal comfort of the occupants, and particularly in the perimeter zone of the building. And so you think about all those criteria, right? Daylight, glare, heat gain, thermal comfort, and then you think of all of the options you have for envelope design with glazing, frit glazing, shading, insulation, so the R values, the U values of the window, all of that stuff creates a myriad of opportunities. And if you have a kinetic facade, right, you're changing that constantly, right? You're making updates to that, or I'm sorry, you're changing the position of those and the performance of that facade in real time. And so, we've developed scripts within Grasshopper. We use an Energy Plus kind of calculation engine, and a Radiance daylighting calculation engine to develop a kind of evolutionary process that optimizes toward the right outcome. And so, we ultimately start from the sort of 35,000 feet level and just looking at solar insulation and looking at every possible surface of a building to really identify, okay, because you're unlikely to put a kinetic facade on every orientation. You're going to focus on where it's going to make the most difference. This is just an example of what I mean by that. And so when, we've developed tools that are for early phase design that look at, say, a module within the perimeter of a building, and then start to create these families of shading devices and glazing types to sort of quickly iterate and optimize around a best outcome. Because these are kinds of decisions that we make as designers very early on in a project design. And so for us, there's an enormous value in being able to look at as many cases as possible to really give the architect as many options as possible. And so, this is just kind of explaining that iterative or that parametric process, and that you can, you have the sort of inputs, orientation, window to wall ratio, shading, glazing performance, and then you have outputs looking at the insulation level, reduction, the solar heat gain, basically, and then looking at daylight and daylight factor in terms of depth of the daylight performance within the space. So this is a tool that we've developed, and it has an interactive component to it that I'm not really showing you, that can be used by an architect to play around with all of those different parameters. The first kinetic project that I did, actually, and I haven't done really a large-scale kinetic project, frankly, but this was a clothing store, a Prada store in Beverly Hills that we did maybe 20 years ago. And what you're seeing on the left is a glazed dressing room. And so this is a sort of electrochromic glass. So when you walk into the dressing room, you can step on a button on the ground, and the glass, an electric current charges the glazing and activates a surface within the glazing that changes the visible light transmittance of the glass, right? So you can go, in this case, you're going from a visible light transmittance of about 60%, which to the human eye appears completely clear, to a visible light transmittance of about 10%, which you can see looks kind of like a frosted glass. You can't really, you could certainly see the outline of my body within the glass, but you couldn't see details. And so this was an example. This is an internal environment, and it's a very early use of that technology. But now, now we've developed glass types like this, that operate like this, that we can use in an envelope to turn on and off performance of the glass in a way. So I really think that this is sort of like the future of our business. And I'll just skip some of this stuff. This is just sort of talking about parametric design. So let's get into some of I'm just thinking we should get into some of the case studies before we run out of time. One of our, so this is most of these case studies are projects that we've completed at Arup. So they're projects I know very well, either because I have been loosely involved in them, or they were completed by colleagues. This is the Beijing Aquatic Center. This was done for the Olympics in 2008. This was actually designed by, I used to work in Sydney, Australia for several years. This was done by our team in Sydney. So I'm sure a lot of you know that project. It was, to me, it was one of the more successful Olympics projects, and it's been converted to a public pool. So it still lives on. But what we're interested, in this conversation is about what that envelope system does. So it's an interesting project because it has this sort of space frame steel structure that envelops the whole building. And then it has an ETFE layer, a facade layer on the inside and the outside. So it's kind of a cavity building. I always think of this building as like taking a coat and wrapping it around the swimming pool, because you have an inner layer and an outer layer to that coat. But what's a benefit of using ETFE, which is basically plastic, is that you can get, it has translucent properties, so you get all of this daylight through it. It's a fully kind of daylit building. But the original concept for the water cube was a kinetic facade. And so what they were thinking, what we're looking at is a section through the outer layer and the inner layer. And this is an environmental diagram for the summer months. And so what you see here is the outer layer of ETFE on the water cube is 2 layers of that plastic material that creates a pillow. And so we're constantly inflating that pillow. And that creates, that puts the ETFE in tension, by inflating it. And so you could literally walk on it, right? People can walk on the roof of the water cube because that tension and the way that it's clamped into the steel frame holds that in a very tight tension. Now the inner layer, so again, this gap here is probably, easily 4 or 5 meters. It may even be more than that. It's quite a large cavity, right? It's like an occupied floor. It's probably, gosh, may even be like 7 or 8 meters. It's quite a large space because all of the structural frame is in that cavity too. So then on the underside of the structure is the second layer of ETFE pillows. And that layer, the original concept was to have 4 layers of ETFE. So maybe I'll annotate. Let me kind of just draw on this. So what I'm talking about is this layer here, right? So you have 1, you have 2, and then you have 3 and 4 inside here, basically in section. And so you're inflating, you have these different cavities, right? You have 1, 2, 3 cavities that you can inflate. And so when I say inflate, the water cube has a whole bunch of blowers and tubes all over it that are constantly keeping the envelope inflated. And it sounds like, well, wait, really, you're running a pneumatic system in the building at all times? Yes, we are, but it's extremely low energy, right? It doesn't take much. It's like when you turn on your hair dryer on the cold setting. It's not really pulling a lot of energy if there's no heat, because there's no heat in that air. It's just air. So in the summer months, what you're doing is if we think about this as 1, 2, and 3 in terms of the cavities, is that you're inflating 1 and 3 and you're deflating the second cavity. You're taking the air out. So those 2 layers of ETFE come together. And the idea was that on those layers of ATFE that you have a checkerboard frit pattern. So frit is white ceramic material that's printed on a surface. You can print ceramic onto glass, you can print it onto plastic, you can print it onto metal, whatever you want, right? It's just and so that's frit. And so what the concept was is that you have one layer of plastic has a checkerboard pattern of frit, and the other layer has an alternate checkerboard of frit, so that when you pull the air out of the second cavity, those 2 layers come together and you have 100% frit on the whole surface. And so what this does is that in the summer months, when you have the sun coming through, passing through that outer ETFE layer, which is really about weather protection, you can see that the radiant energy from the sun, it only cuts about 5% of that energy out, right? Some of it's absorbed, some of it's reflected. Most of it is transmitted through that envelope. But this inner layer, then you have that full solid frit pattern in the inner layer. It actually reflects the bulk of the remaining heat. And so what you end up in terms of the heat gain into the water cube is like 5%, right? So that was the concept for how that would actively respond to the environment. So then in the winter months, I guess I have to erase that, don't I? Otherwise it'll be there forever. In the winter months, it's the opposite, right? You push air into that cavity and you open it up. So then you actually want heat transmission through the ETFE into the space as free heating. So in that case, you are allowing 50% of that radiant energy into the pool. Now, the other thing that I didn't talk about is that there are vents on the water cube that vent this internal cavity, the structural cavity. And so in the just to go back for a second, In the summer months, you open those vents because you're exhausting that cavity, right? As that 95% of heat gain starts to build up in the cavity, you're exhausting that air. So you're collecting it, and then you're removing that heat from the space. Where in the wintertime, you close that vent because you want to keep all of that heat in there like a blanket. Now, the other thing at play here, that's this section over the pool. But the other thing at play is that you have a moat around the water cube. So you're bringing in water, you're bringing in air that's been cooled through an evaporative process across that moat. So you're bringing in cooler air at this gap here at the cavity. So in the summertime, you're opening those vents and bringing in cool air, right? It's not cold air, but it's cool air. And so what you're getting is a kind of natural stack effect within the cavity, right? As that cooler, moisture air comes into the cavity, the sun heats it up, right, and dries the air out. And as that air heats up and dries out, it becomes, through buoyancy, it will rise, right? So that's what we mean when heat rises and we have a stack effect ventilation. Is that we're taking the moisture out of the air so it's lighter and it will rise effectively. So you have this very passively designed envelope that actually works very well. And then in the wintertime, of course, you close that up. So that project is in the book as a case study. This is another one this is a children's museum in Pittsburgh. And the architects for this project are Koning Eisenberg. They're a firm here in Los Angeles. And we actually worked with them on this project as the structural engineers. But this is an installation that they collaborated with an artist named Ned Kahn, who does these kinetic sculptures. And so what they were interested in is that they had a very kind of basic building and a basic kind of curtain wall system. Is that with the Children's Museum, they wanted to create something that would really appeal to kids and something that would kind of inspire them. And what this is it's just a very simple external structure that connects to the primary structure of the building. So it's like a space frame, basically, that acts as an envelope, a kind of secondary envelope. So the details of this, the design of this isn't too complicated. But what they did, what one of Kahn's, the artist's ideas was to take these kind of plastic panel board material and create flaps. So what you're seeing here, this is a prototype looking at these little flaps that are pinned into the system. And so when the air moves across the facade, the flaps just move, right? So what you do is you're starting to register the effect of the wind across the envelope, right? And looking up, you get this sort of repeated pattern, and you can see where some of these flaps have moved. You can see a very simple structure. Whoops. And so, people ask, well, why do you include this? Because it's, is it really a kinetic facade? You're not manually moving anything. It's right. It's passive. But the point I make is that you're registering environmental change with this, but you're also it's an effective brise soleil, right? This is a classic architectural solution for shading design that works very well to shade the glazed curtain wall that's behind it. So, to me, I just put it into the category of a kinetic facade, even though it's not, it's more about performance, or what do I want to say, a kind of social performance in a way than it is environmental. So this was a project that it was a competition that I worked on with an architect here in LA, Jennifer Marmon. This was for a library for Helsinki. This was an international competition. We didn't win, needless to say. But her idea was, how do you create or creating this this kind of uniform, consistent glazed envelope, but then really thinking about variation within the uniform envelope. And so you can see we sort of had this idea of how do you start to close in and open up this building depending on what is necessarily happening on the interior, right? So this library had a crazy program. It had like cafes and a sauna and books and an auditorium. There's a lot going on in this building. And so we wanted to create a sort of consistent design agenda that then had a lot of variability in it. And obviously you have different orientations. And so each orientation kind of starts to operate in a different way based on the position of the sun. So one of the things we were thinking about was the idea of the oculus in architecture and thinking of each of these, thinking of the envelope as an oculus in a way to register the sun. The thing about Helsinki, right, when you look at the sun path diagram, and again, this is the Pantheon in Rome, which this just came out of design conversations, right, is thinking about the oculus and the Pantheon, is that what works quite well about the oculus is that the sun in Rome, of course, is much higher in the sky. So you have beautiful sunlight in Italy. But it's actually, this is very similar to the sun path diagram in Los Angeles, for example. But you have, in the summertime, you have very high angle sun. Even in the wintertime, it's not too low in the horizon. But in Helsinki, of course, the sun is never that high in the sky, even in the summertime, even if the days are extremely long. But in the wintertime, the sun, you don't get much sun at all in the wintertime, and it's so low in the horizon that it hardly registers, right? So you think of the sort of the almost total darkness. And so an oculus on the roof of a building doesn't actually make sense. So, here's Rome, for example, right? Is you get this great register. We were rendering the Pantheon. You get this great registration of the sun, but for Helsinki, you really have to think of the oculus as a vertical surface as opposed to a horizontal surface. So we thought, well, what happens if we just rotate that oculus and then we repeat it as a facade pattern, and really think about how we can modulate the quality of the sunlight through the facade and really open it up, right? So we created this distribution of apertures within the envelope. And so that was the architectural pattern that Jennifer created, and looking at where do you have 10% openness to 50% to 90%, right? Because in places like corridors, you might want the facade as open as possible. But for obviously a place where you're storing books or periodicals, you might want 10% openness. And so it's just to segue for a second, this is a strategy that we did on another library in Seattle. This is a project I worked on maybe 20 years ago. Yes, I really am that old. And this is the Seattle Public Library. This was with OMA and Rim Koolhaas. But this is a similar kind of strategy from an envelope perspective, is that you have a uniform diagrid envelope, right? So this is a steel structure diagrid that then has a glazed facade, the little diamonds basically that repeat across the entire surface of the exterior surface of the building. But when you look closer, you can see that there's variability within the facade, right? So you can see on this vertical surface here, this is mostly clear, pretty clear, but then you can see here, these are actually our mechanical system. So these are vents, but then you see in this panel here, you see that there's a kind of haziness to it. And that's because within that facade panel, we have a metal mesh that acts as an internalized shading device. And so parts of that building even though it appears to be a consistent envelope, actually have that variability, right, of openness and sort of improved solar heat gain. Let me erase that before we go on. And so with the library in Helsinki, we kind of developed a facade typology, and I apologize that it's kind of hard to read, that was a pretty thick envelope because of the extreme environment of Helsinki. So we were looking at having an external, this is in plan, right, is having an external piece of glazing and then an internal performance piece that would create a double skin. So you have 2 layers of glass, ultimately 3 layers, right? If you think of, or 4, if you think of the out as 2 pieces of glass and the inner layer as 2 pieces of glass. You know, the idea is to create, it's very similar to the water cube, right? And we're thinking about creating a thermal blanket with that cavity around the whole building. And then the variability happens with this inner panel, which is the oculus. And the initial concept for that, at least in our competition, was to make the oculus out of a vacuum formed plastic material that could be clipped into the cavity, right? So it would have a level of translucency to the oculus, but then you would have an opening that would be fully transparent, right? Well, it would be a void. And that you could have that repeatability. So you get what could start to read as a dynamic envelope, in that you have a lot of variability within the consistent uniform frame, right? That was the concept, how to do a kinetic facade without too many moving elements. I'm just conscientious of time. And I have maybe 3 more case studies. This may be the least interesting. So I might skip, if that's okay with you, to the ones that are a bit more interesting. And so we don't take too much time here, because there's a lot of aspects to that one. So apologies for that. That one goes into a bit of a deep dive around the design process, which I think we've kind of covered. This is a project in Korea that's actually built. It's a research facility for a chemicals company. And we were working with the Murdad Yazdani is a Los Angeles architect. He was the design architect for this project. And the concept here is that, so it's a research facility with laboratories, but the perimeter of the building is sort of like large collaboration spaces and corridors. And what the architect wanted to do was to have it a lot of glazing, of course. I mean, that's what you're seeing in a lot of these projects is the architects we work with like to use glass a lot, which doesn't always work everywhere. But in this case, Korea, Seoul is a fairly, I don't know if I would say temperate climate, but it gets hot there, it gets cold, but it's not extreme, I would say. But you have 4 very distinct seasons. And so there's a real benefit to thinking about a building that could dynamically change its position in relation to the seasons and the environment. And so the idea was that you create this external shading system that's almost like a pleat that collapses and opens, right? So you have the glazed, you have the sort of fully glazed area, whoops, here. Oh, I don't know why. Okay, sorry, I'm trying to annotate that, and it doesn't want to let me. Okay, well, anyway. And then you start to close the pleat, so to speak, and it cuts the glazing down to just a simple kind of strip. And his concept was really just looking at an umbrella, right? When you push the little device of an umbrella, right, it extends that frame out. And it's really the same kind of principle, is that how do you have like an umbrella frame, but happening kind of perpendicular to the building. And so you end up with movement on a y-axis, right? There's really no movement so much on an x-axis. It's stretching and it's collapsing, stretching and collapsing. And so you can kind of see what I mean in terms of that perimeter space being fully glazed in the little image there. That wouldn't it be great if you could pull a shading device across it? And here's my issue is that you've probably seen, certainly in Indian architecture, the idea of an external screen and a shading device or a brise soleil is a very common kind of design approach in India, because what you're trying to do, right, is to minimize the heat gain in the building. And so a screen in front of glazing works quite well for that. But what a screen does is it also cuts down your view, right? It impacts the visible light transmittance. It might reduce daylight as well, even though it's providing the benefit of reducing the solar heat gain. And so in this case, with the dynamic aspect to the envelope, is that the screen can pull away and give you that wide open space when you don't need it. And I think that's one of the key benefits to this kind of approach. And so, obviously in Seoul, it makes sense to focus the system on the south facade, because that, in this case, in this building, is getting the most solar insolation. So those studies happened to really focus where the device should go. And so then the architect did a kind of, trying to see if that video works, and it doesn't. Yeah, sorry. But the architect did some proof of concepts looking at the different components of the building to make sure that that these open and close, and so there was a lot of prototyping done, and then this is a mock-up of the system. So this is always kind of a bummer of a project, because at the end of the day, they took the active component out of the system and made it a fixed element. And then somebody needs to mute. All right. I can mute it again. Okay. Hopefully you can hear me. So I think I have two more case studies, and then I'm happy to take some questions, as I know we're kind of out of time. This is a research project that Arab undertook with the German government. This is in Hamburg, and it's called the bioreactive facade. And so it doesn't look from appearances, it's not like the most spectacular project in the world. But what we're interested in are these little panels here. And they're really the active component of the project. And so I say this was a research project because the research question was, can you make an envelope system that uses the sun's energy to create algae? And then you use that algae as a biomass feedstock for a kind of a closed loop energy generation system. Right. So when I say algae, what we're really talking about is pond scum. Right. So like if you have a pond out in nature and there's not consistent water movement in that pond, right, then you will start to develop bacteria and algae on the surface of that pond, and that bacteria can grow and grow and grow. And that's basically what we have here, right, is that we have a closed cavity of the envelope. And so this is two sheets of glass that completely close off the cavity. And then you have these pumps that are circulating water through each of these panels. And so all you really need to do is introduce the right bacteria or algae into the system, and the heat from the sun will actually warm up that system and encourage growth, right? And so the algae just multiplies as it goes through the system. That's what it looks like. It looks, you know, kind of disgusting. And so this was part of a you know, an integrated project, right? And so this is saying, how do we use an envelope to create a biomass, and then we feed that, we convert that to energy, basically, right? We might burn it to create heating. We might burn it to create electricity. We couple it with other systems in the building. So this was completely, you know, speculative research to really see, is this an option for our buildings? Could all of our buildings start to generate energy this way? Because I think what they were trying to do is to find ways to not only use solar photovoltaics, right, which you see in the upper right here. Is that, are there other ways to create energy around a zero carbon? And so ultimately the installation looks like this, right? The panels are installed in the exterior of the building. They act as a shading enclosure for the terraces on the outside. So it's not actually the envelope of the building, but it's a shading device that you can sort of roll back and forth. I think they do move a little bit, but you get this kind of, you know, if you live there, this is a residence, by the way, a multifamily residential building. And so that would be your view. And you might wonder, you know, what are these little dots in there? And they're just little balls that are pushed around by the water inside the cavity, and they keep the glass clean. So it's sort of a self-cleaning project. And then, oh, I take that back. I guess I have two more projects. This was a project that was a competition with the architect Doris Sung. She's a friend of mine here in Los Angeles. This was a competition for an installation or a pavilion in a plaza in Tel Aviv. So this is an environment, right, that's very hot. It's Mediterranean, so it's not extreme, but it's definitely about improving outdoor microclimate around shading. And so what Doris's challenge to me was when we started this project is, hey, Russell, I want to create like a breeze on a street, but I don't want to have any active technologies. How do I do that? And so what you're looking at is kind of a balloon. And so we had the idea of an inflatable structure that would be supported by this kind of metal undercarriage. And the metal undercarriage is actually two metals. It's a thermal bimetal. So it's two metals with different coefficients of expansion that are laminated together. And so what that means is that when you expose a thermal bimetal to the sun, it will, as one of the metals starts to expand, it will pull the other one with it, right? So this is about creating a kinetic structure that only uses solar energy to change. And so I'm interested in this project because it required no electricity, right, to get that kind of dynamic performance that we were after. So apologies, these are a little blurry. But the thought was that metal undercarriage would do a couple of things, right? One, it would shield you from the sun when you're under the inflatable. But then we thought we would create a cavity in that inflatable. So that inflatable would have a hole in it, like it's kind of like a donut, except a very small cavity. And we think of that cavity as a solar chimney. And so what the thermal bimetal undercarriage would do is that as the sun came out, the metal would start to fold up and create like a solar reflector field, and it would concentrate energy on that internal chimney. And as it concentrated energy on the chimney, it would drive a stack ventilation process, right, where it would actually pull air up through that cavity and exhaust it at the top of the inflatable. So that was the concept, right? We tried a lot of mock-ups of this at various scales. and trying to replicate it. And I have to say, a system like this, it's not like you're going to sit under there and you're going to feel a breeze blowing across you. But there is we could actually establish an energy transfer from this enclosed, lower area to the upper area. But it was very, it was very small, right? It wasn't a radical difference. And so the more we thought about it, the more we thought, well, how hard is it just to put a little fan at the top and put some solar panel, laminate some solar panels on the inflatable and actually just use the solar energy to drive a little fan. I mean, you think about the little fans you hold that they sell, for sporting events that you can hold a little fan in your face. That's basically, it doesn't require a lot of energy. And then it starts to create this microclimate under the inflatable that pulls the air up through that kind of oculus there in the middle. That was the concept, and that we never built. So my final project is a kind of massive kinetic facade that our office in London, Arab's office in London, was involved in with architects in Abu Dhabi, and this is the Abu Dhabi Investment Council headquarters. They built 2 towers because I guess they decided just building one really big one didn't work for them. I don't really know. I wasn't involved, but what you can see is it's a glass tower, and then you see these shading devices on the outside, right? And so what we're looking at is the north elevation, because the shading wraps around from the east to the south to the west, right? So what you're seeing over here is the west. This is late day sun. So you see a little bit of sun on the glass, but not much. And so in plan, looking at an axon of the plan of the tower, right? It's an office building. And so you have a pretty hefty core, and then you have all this perimeter office. So environmentally, it works quite well, right? It's a shallow floor plate. You can effectively daylight this whole zone. It is Abu Dhabi, so it's an extreme climate. And so it's mostly in cooling mode, right? We're pretty much always air conditioning this building. There's no natural ventilation in this particular building. And then you see the shading devices on the outside of the facade. It's really like a screen on the east, south, and west. And so the concept was this is a pretty what do I want to say, high performance envelope, right? You have a conventional curtain wall system here that's actually the envelope, and then the shading screen is connected off of the structure, right? And then is a secondary structure that's at least a meter, maybe 2 meters off of the envelope. And so you actually have access on the outside of the envelope of the building for maintenance, right? So think about it as cleaning, and all those sorts of things can occur between the outer layer and the inner layer. And so the concept for this shading screen was something that is kind of a common shading device in architecture, in Arab architecture, and it's the idea of the mashrabiyya. And so what this is kind of like when you're thinking about the Korean project I showed, kind of like the umbrella, is that this central pivot here, piston, is really the actuator that pulls and pushes the screen open and closed, right? So this triangular element then collapses in and or opens up, depending on whether you need shading at the perimeter. Whoops, didn't realize the yeah. So here, this was a mock-up done. So this entire screening system was manufactured in China by the facade company Yuanda, and this was their initial mock-up and their prototype test. So it was put under pretty rigorous testing to ensure that it would actually be able to open and close thousands of times, right? Because we're installing this on a building, and under, that will be subject to quite extreme conditions. So it needed to work, right? So what you're seeing is that central piston is pulling in, or I'm sorry, pushing. As it pushes out, it pulls the panel in on the sides, right here. And so what the benefit to this was reducing the demand for air conditioning in the building, right? So this is just because I'm a dork and I do energy models all the time. This was the outcome of the energy model in terms of reduction in cooling demand, right? So things like elevators and power and lights, they're definitely more efficient than a traditional building. But the real gain is in the reduction of cooling. And so they save something like 20% of their air conditioning costs by having this significant shading system. So this is the system in construction. So you can see these are quite large, right? This is a typical floor here. And so each one of these is spanning across that floor. But what you see in this condition here, where they're open, is that you get a lot of daylight through there, right? So you get the views, you get the daylight that you want from a human occupancy standpoint, right? So the indoor environmental quality benefit is there. Here it is. Here's more of it constructed. You actually would never see this in real life because the way that the system is controlled is thinking vertically, right? Depending on the orientation of the sun. So the sun, you can see, is on the left side of the building. So all of these panels on the right side should be open, right? Under normal operating conditions, they would be open because you don't need to provide any shading. So this is truly a kinetic facade. And when you look at that in terms of performance, right, here you go. It actually moves quite fast, right? It's not a slow system. But you can go from completely open to a completely shaded building. And it has a kind of kinetic performative aspect to it. So maybe you know this project. But it's to me, it's kind of the most radical in terms of the realized kinetic facade projects. And as you can imagine, it's very expensive to build. So I think that's one of the reasons you don't see a lot of it. So that's my final slide, and I'm happy to take some questions if you have time for that. I can just leave this playing.
So, yeah, any questions?
Hello, can I ask a question?
Yes, please.
Yeah. Sorry, I was muted by the host or somebody. So I'll go again.
Okay.
Make another attempt at asking my question. So thank you, Russell, for the highly informative presentation. I wanted to understand the ideology and philosophy behind this building in Abu Dhabi. We have a glass facade and then we come up with another skin, another layer to kind of prevent the heat gain. Is it? Isn't it ironic that we first do a glass facade, bring heat in a place like Abu Dhabi, and then put a second skin on the building, which is flappable, which is moving, which is great. The technology is awesome. But had we reduced the glass usage in the first place, perhaps the second envelope could have been smaller or not needed at all. So your thoughts on that? Thank you.
No, that's exactly the question I would ask, right? Is why? Why are you creating a problem and then patting yourself on the back for solving it, right? Because it's entirely a problem created by the design. But I'm sure however I answer that won't be satisfactory. But if you think about it, this is basically a building for people that work in finance. And if you look at banks and you look at financial services companies around the world. Where are their offices? Right, they're all in glass buildings, and so I would just say from an owner perspective, there is an expectation that this building will be like those, right? So when they looked at projects around the world, they were probably looking at, I don't know, I can't think of any examples off the top of my head, but look at any of the buildings in Hong Kong or London or New York, right? Look at the financial centers. Is it the kind of people that work in this building are people that probably have worked their careers in London, Hong Kong, and New York, in Tokyo, or whatever? So I would just say that there's a kind of cultural expectation that to have a similar type of office, and that gets embedded really strongly by the client. This is kind of the world we live in, right? And it's sort of a hangover of modernism, and that in the project of modernism, at least in the way that it was practiced in the post-war era, was to think that you could design a building and build that all over the world with no variation, right? And air conditioning would always save the day. And that is definitely an old, kind of outdated approach to design. But there's a lot of pressure, I think, on architects to deliver consistency in terms of the quality of the experience in the architecture for certain classes of people, right? So do I agree that you should be doing an all glass building in Abu Dhabi? I don't. And so the reason I include this case study in and it's in the book even, is not to say that I think that this is appropriate climate responsive design, and that this is a good use of our resources, because I don't actually think that it is. But just looking at the technology of the shading device itself, that was my interest, is that this is probably the most work, research, and fabrication that's ever gone into a kinetic element on an envelope. And I think there's a lot to learn here, actually, because I think this kind of system, there are smaller, better designed projects where this kind of system could actually work equally well, right? It doesn't have to be a glass tower. And I think it's important that as architects, we learn from this and we understand how we could achieve something like this on a building that's actually climatically responsive and responsible, right? So yes. I don't want you to think that I advocate for this. I totally agree with you.
Yeah, I'm fully satisfied with your response. I 100% resonate with what you said. If the idea was to create an iconic element for a financial, organization, then definitely this building is iconic. The second part of my question, Russell, is that as somebody who deals with energy in buildings, you always make trade-offs. So the trade-off that you are making here in terms of preventing the heat gain in the building with the second skin, with the second layer of the facade, versus the mechanical energy that goes into operations of this facade, contraction and opening. Would you like to talk about that? Was there a trade-off for the designers, and how did they, arrive at that decision that how much of energy actually goes in operating this facade, for the life cycle of the building?
So that's a good question too. And I would just say, because what you're seeing in the video, right, is just, and maybe you're getting sick of seeing that. I'll just switch. But it's like everybody's like mesmerized. But keep in mind that these only open and close, right? They only open once and they only close once, right, per day, right? So otherwise, most of the time they're open. And then when the sun comes up and starts to come around, they close. And then as the sun moves around again, they open. And so you're talking about 2 moves a day. Okay. And the energy for the actuator is super low, right? Like you trust me, plugging your phone into the wall in the building is going to take more energy than the facade problem. I mean, I don't mean to be so cute about it, but it's a negligible process load, really. It doesn't take much energy to do that.
Right. Maybe it was the video that got us thinking.
Yeah, it's not always doing this, right? It's just closing and then opening, and that's it.
Right. Thank you, Russell. Thank you. Thanks.
Yes, sir. Mohan sir, you had a question.
Yes. In this Al Bahar Towers in Abu Dhabi, we had a chance to see this. It looks very attractive. My question is there are so many other buildings adjacent next to this Al Bahar Towers, and they're completely made with glass. So could you compare how much energy this particular type of building would be saving when compared to buildings which are just built totally with glass? Because many of the tall buildings in Abu Dhabi are totally built with glass. So just like you take the Empire State Building, today this building has been retrofitted and it has become one of the most energy efficient buildings in the world. Earlier it was energy guzzler. So maybe from that point of view, how much energy this particular kinetic device is saving, that could be a plus point for this type of stuff.
So,
how much it saves on air conditioning?
So in the energy model that was done for this project, comparing, say, a code compliant building to the design of the actual building, they modeled a 20% savings in air conditioning. But keep in mind that's looking at, so a code compliant building typically would have a window to wall ratio of 40%, right? So 40% glazing to 60% opaque is what and the ASHRAE 90.1 energy code typically sets as a baseline. And so this tower, the ADIC building, probably has a window to wall ratio of 70%, right? In terms of glazing to opaque surface. And so the shading device basically reduces the heat gain to the point where that 70%, that additional 30% window area over the baseline building doesn't actually impact the performance of the building. And so the shading device is absolutely critical to allowing it to have that amount of glass. Now, comparing it to the other buildings you see in Abu Dhabi, as I'd say the key difference is that the curtain wall system on this project, the glass type in it has a much higher visible light transmittance and a higher solar heat gain coefficient, right? So instead of like what you're seeing on a lot of other towers in Abu Dhabi is a solar heat gain coefficient of say 10% maybe, or 12 or 14%. It's highly reflective mirror glass, right? And so when you go into the interior of those buildings, that reflective, higher performing glass also has the effect of reducing the amount of daylight entering the building, right? So you can go in a building in Abu Dhabi and it seem very dark in the building when you look outside because it's like you're looking through sunglasses. Where this building, one of the reasons they put the shading device in is because they wanted the glass to be much clearer. They wanted to bring more daylight in. So the visible light transmittance of this glass, I want to say, is like 45%. It's pretty high when you compare it to a mirror glass building where the visible light transmittance, might be 20%, right? Might be 30%. It just starts to look dimmer and dimmer and dimmer on the interior. And so that was one of the key drivers, was to improve the quality of the daylight for the interior. I see some other questions in the group chat. Yeah. I don't know if you want me to take a look at some of those.
Yeah,
Bandhan, okay.
Bandhan has a question. Bandhan.
Okay.
Yeah.
Yes, sir. Thank you, Mr. Russell, for such a wonderful presentation. But I have one question.
Yes.
What are the major limitations you have found while designing for this kinetic facade? Or are those limitations common for all the projects, or it differs from project to project?
Well, I think the primary limitation is cost, right? And that this is not very little of what I've shown you today is anything that you can buy off the shelf, right? Most of these buildings are completely bespoke designs, and so it's as soon as you introduce the kinetic element to buildings, you're also introducing another energy system. And as soon as you have an energy system, right, it can, you have to maintain it. And so there's not only a first cost for the system, which maybe you can find ways to work around that, but there's that operational and maintenance cost of keeping it up, right? And so you look at this project in Abu Dhabi. They have had a large budget for the project. They could afford it. They have significant revenues that they manage. Just the people that work in the building do. So it's like maintaining this building is also has an expense to it that not every building owner is going to want to support. Right. So I think that's probably the biggest limitation. I think the second biggest limitation is just that very fact that there aren't technologies that are off the shelf, right? That if you are looking at a literally kinetic building, you have to develop, you almost have to develop that yourself. I mean, you can find louver systems that might move and stuff like that. You can find metal scrims that might have an actuated panel that goes from closed to horizontal, right, like a flap. I've certainly seen those on buildings, but I think if you want anything more complicated than that, then you're looking to have to work with a facade fabricator on a completely bespoke system. So the reason I was interested, like I said at the beginning of the lecture, the reason I was interested in the topic is because I think that it will only get cheaper for us to do stuff like this, right? It will get, when you have little control devices that cost a nickel, it's like, then why not have a responsive facade element? Why not design our facades to be responsive, so they can adapt to changing conditions and our buildings can perform better? Like, I feel like this is one of those things where architecture is way behind in terms of where technology is moving. And I don't want you to just think that I love technology and we should just do it for technology's sake. I think it always has to be motivated by a design case. Are you improving the quality of the environment for the people in the building? Are you improving the environmental performance of the building and reducing resource consumption, right? I mean, like, you have to look at that bigger picture. Otherwise, it's just a gimmick, right?
Thank you.
Did you study the trade-off between the capital cost of the specialized glass and a glass which is very normal with this kind of a scheme? Did you do that exercise in the trade-off of the capital cost?
I did not for this. So I wasn't involved in this project personally. So I don't have that off the top of my head, but I will say just generically on buildings that I work on, anytime I look at working with an architect to provide a shading system on the outside of a building, we don't look at that as just the cost of the shading alone, right? You have to look at everything as an integrated system, right? So there's the shade, there's the glazing, and the rest of whatever the curtain wall is, but then there's the internal environment, right? Electric lighting, and there's the mechanical system, and so all of that I look as an integrated cost model. Because if I take the shading device off the outside, and then that might mean that my mechanical costs go up, right? My operational costs go up. But it might mean that I need less electric lighting. But to be perfectly honest, with LED lights, the lighting power in a building is a drop in the bucket now from what it used to be, right? So that's not as much of a driver, but it's really about the mechanical system. And so I would never, when I do a life cycle cost benefit study of these systems, I'm always looking at that integration of the mechanical facade and the shading device as a complete system.
And definitely this kind of a facade will be affecting the ambient temperature outside the building also. Maybe this would be a very positive aspect when you actually take into consideration the whole setting of the building itself. When you have a reflected glass, definitely it's going to heat up the ambient air around the building. So maybe this would also be a positive thing when you look at that.
Yeah, no, that's a good point. I mean, exterior reflectivity and urban heat island is definitely an issue in a lot of our cities. Yeah, that's a good point.
Yeah, Hema, do we have any more questions?
There were a few in
one
the
more,
chat.
yeah, one more, Russell. Like,
Yes.
how do you think that we can introduce this kind of a knowledge at college level for students of architecture? Like, how do we do that? Like, at what stage would it be suitable for us to talk about this to the students of architecture?
Well, I teach an environmental systems class, and we don't really get in my particular class, we don't get into envelopes too much, but in terms of different system types. But to me, I just think it's important to understand first and foremost the basic principles of physics at play here, right? Because what I see with students in the various places I've taught, and I don't mean this as like it's probably a bit of a generalization, but is that I've been in plenty of architectural crits in schools where a student has proposed a system and then they don't know why it's there, right? They can't actually explain the physical reasons, the environmental reasons for why their building looks the way it does or does what it does. And so I just think if you shouldn't really even start to look at these kinds of systems until you have a really firm foundation in understanding heat transfer, in understanding the relationship of orientation and massing to the sun, in understanding the quality of daylight and the benefits of daylight in the interior. Because if you're not motivated by those very fundamental principles, then you can end up with a system that's a gimmick, right? That doesn't really do anything except move around and look fun. And so we looked at a lot of projects that were kinetic projects that we felt like did not really meet the criteria of the book, because we were interested in the environmental aspects. And if there was no environmental motivation for the design, then it didn't make sense. But to me, you could easily do an entire studio around this if you wanted to, right? And make that a design challenge. I think within a studio setting would make sense. I think to get into the technology in any detail would probably make sense maybe for a graduate program, if students were really motivated for that kind of research. But to be perfectly honest, I feel like we have so many challenges in architecture that this will always be a niche, I feel.
No, actually, in the first part of the presentation, I was feeling like it seems more like a passive architecture elements that you were actually talking more. But as the presentation progressed and as the complexity of the buildings and the efforts you have done, you showed us, then it made little more sense about kinetic architecture. But as you said, initially it is more of a passive architecture that we have to look, and then if it is beyond that, then that's how we should start. Yeah, that is true.
Yep. And I guess there's one, I'm looking at all the questions in the group
Yeah,
chat,
yes.
and there's one question that I think we probably haven't answered that I would just,
Sure.
that someone is asking for examples of passive kinetic envelopes for high-rise buildings that don't use mechanical or sensor systems. You know, and there's a great book that just came out this summer called, let's see, it's Bioclimatic Design and Modern Architecture. Is that the name of the book? Let me, whoops, no, I didn't want to do that. I can't remember the name of the book, but it deals with kind of modern architecture and really digging into shading systems in modern architecture. And it looked at a lot of high rises in Rio de Janeiro in the sort of in the post-war era, like the 50s and 60s. And a lot of that work was new to me. And I think that it would probably be worth looking at some. I mean, I can certainly think of modern examples. We work a lot with the architect Tom Main and his firm Morphosis. And we've done high rises with Morphosis. Say like there's the federal building in San Francisco that we did with Morphosis in the early 2000s, and that has a metal mesh brise soleil on the outside of the building that acts as a shading device, and it's fixed. It's not. There's nothing fancy about it. It hangs on a frame, but that's a naturally ventilated high rise, and so the windows it does have an active component in that the windows automatically open and close to let fresh air come in to the high rise. So it's about it's not the biggest high rise in the world, but it's certainly a good case study to look at. That's the San Francisco Federal Building. And there's a lot of published material for that online. So you can actually find case studies about how well it performs from a natural ventilation standpoint. But it has a brise soleil on it. I think that's a good one to look at. So the other one, yeah. So I'll just leave it at that. Yeah. So I think everything else we've probably kind of touched on. So I don't.
Yeah. Yeah. Emma, anyone else?
Yeah, one last point, Sunil.
Yeah, yes, sir. Please, sir, continue.
You have talked about the modern systems, the kinetic systems, but I think the basic inspiration or the origin of these systems has come from the mashrabiyas. Like mashrabiyya was used by Hassan Fatih in the 1940s. That was even before the word sustainability was coined. So we had a chance to see some of his buildings, mud buildings in Egypt, and all these fixed mashrabiyas. These are screens which are fixed to the windows, and they reduce the glare and keep the interior very cool. So all these design of these mashrabiyas was done without any structural calculations. It was all done intuitively. So basically this intuitive knowledge is what needs to be studied by architecture students, as a foundation. And then later on, it's just an adaptation of that. That's what Hassan Fatih did. He took all the vernacular systems and he reinterpreted them in the modern context. So the students can learn a lot about these screens, mashrabiyas, because you use the word mashrabiyya, it's a vernacular word, from which
Right.
this entire thing has come about.
That's such a good point. And that's where I start my class every year is and we actually look at a book that you may be familiar with called Architecture Without Architects.
Yeah.
It's by Bernard Rudofsky. And I always tell my students to buy a copy of it because it looks at vernacular architecture. And of course, vernacular architecture is the best environmentally because people really know the climate and the weather in their location. And architecture emerges from that response, right? that elemental response. And that's why it's always about first principles, right? It's always about just the first principles of physics and really understanding, how you use local materials and local traditions. You have so much to learn from architecture like that. And I completely agree with your comment. Thank you.
Yeah. Right.
All right. Well, hey, thank you. Thank you so much. I really appreciate being able to talk to you. I apologize again for having to join late this morning.
No, thank you. Actually, we should be very thankful for your presentation and for taking out this time. And we were a little bit there was a little bit of anxiety as you are not joined. That's all. So I gave a call to you also.
I know, and I'm sorry I saw that. I was trying to get online.
Thank you so much, Russell. And it was very, very a very good documentation of the work that you have been doing for such a long time. And we all definitely are getting something out of this presentation and inspiration from this presentation. Thank you so much.
Right, good.
Most of
the
participants are teachers. So that is how this can trickle down more easily and more fastly, because if you if a teacher knows, then there is so much of scope for it to disseminate the knowledge. Yeah, thank you so much.
All right. Well, hey, thank you,
Mr. Russell. Thank you.
Thank you, everybody. Have a great day. Stay safe. Stay healthy.
Yeah. Thank you.
Okay. Take care.
Yeah.